This is the view of the model as we started in the previous webinar. It consists of two buildings with a connecting structure, and nomenclature are beams and columns. At this point, we're ready to start. For the sake of saving time, we are having the model just recalled or restored, retrieved from the file. Now we see that the mesh is completed. The mesh has all the properties and all the section properties and material properties. All that is missing is the loading and constraint. This webinar is analysis. That is, the shown structure has already been given to the analyst as is or proposed. And what we do today is constrain at the base and apply the necessary loads for analysis. We have the, by default, the gravity load is there. Now we will demonstrate how to apply the loads. Now we're going to create a load group and spectral load. Now we're going to create a surface load for a plate. We will call it the simple name pressure. Just pressure load. We could have different types such as points, moments, linear. Now we're going to apply surface load. We've got temperature. Now we're going to define a surface load. And we're going to place it on an arbitrary surface that will serve as the basis for the rest of the surfaces to be loaded in reference to it. Now we select the surface onto which we want to apply the basis loading. And the direction is in the negative vertical -1z. A load of 125 psf. We can see on the left the load information for the basic surface. We can see it graphically in two fashions. One is as a lumped symbol representing the surface, and as a distributed load onto the nodes. Notice that the green arrows represent the load direction vector. Now we will invoke the feature Python, which is a scripting language built into CivilFEM. Of course, it's a more effective method of loading. Now we have already selected the areas onto which the loads are created or apply. Actually, for the sake of saving time, we have selected them prior to the presentation. Now we're going to open up the Python script editor. And we will search in the file the script we created. We look at the file, and as you can see, it's very versatile because all we have to change is one single number, which is the 125 live load. This load will be applied automatically in all the horizontal surface plates. And all we have to do is run the script, the green arrow, and you can see the resulting loading as it goes through all the surfaces. Now we can see how the load is being applied and displayed. Now we will hide the Python script editor to visualize the work best. Also, we have to apply the constraints. But first, we're going to change the name of the load because of new ideas that came to us. Now we see all the applied loads. To all the surfaces pertinent to this analysis. Now we're going to convert the live loads to lump masses with a factor of 60%. Now we're going to define a load spectrum. CivilFEM can allow you to easily define spectrum by the user with a few parameters, and also using code. In this case, we're going to display graphically the spectrum we just defined to make sure that we have the intended spectrum. There you go. Now you see on the left red parameters that will tailor the shape of the spectrum based on design requirements. We apply the typical structural damping, which is 5% of critical. And the method is RSS, root square, some of the squares. And we just select 12 modes of vibration because the spectrum will not exceed the 12 modes. Now we're going to define boundary conditions. We're going to call it support. These supports can be visualized graphically very easily. We take an elevation view and then we select all the points at the base of this building onto which we're going to fully constrain all degrees of freedom. Now we have selected all the foundation points or points at the bottom of the model. Now we'll see graphically these supports. Now we can see them. You notice that none is missing. Now all we have to do is create the low case combinations. Now I'm going to create a low case which has the default dead load and live load. But dead load will be self-weight. We just place a name. Now we add self-weight and live load. If necessary, CivilFEM allows you at this point to change the load factor from unity to a non-unity value. Now that we added the loads for this run, we also need to load the constraint. Now the low case is created as intended. Now we have the second low case, which is the spectrum and constraints. Now we call the spectrum. And we just add the case of spectral loading. Now we add the boundary conditions. So you see that loading is actual loading and constraints. Now we have both cases created as we had intended. Now we'll demonstrate the created cases. These are the loads and constraints. While the program is ready to be executed, the model, now we specify some parameters. Here we see we create activate model results. It has to be activated. We initiate the analysis and just it's asking us to save the file, and then the execution begins. At the bottom we'll see the progress of the solution. Even though the model is relatively large, the analysis will result promptly in a laptop computer. CivilFEM is a precise program, validated with known solutions, and reliable. Since it uses a well-established MSC mark solver. In this webinar, we have an additional presenter, Ronald Saya. Now we'll see the results. We're going to look at the file for the results desired. These are all the results. We want to see this first one, live load and self-weight. And we select notice that we can select any unit system. We want the average of results, the deformed solution. And here we have the results. See on the left-hand corner is a Z component of displacement in inches. As you can see, the maximum displacement is 0.4 inches in the blue zone. Now we proceed to see all the results. Where we can see moments and forces. Now we seek through the list of results, moments. We could see the shear forces as well. In this case, we're going to plot the moments. and foot-pound. Here we can see the bending moment diagrams. With the maximum values in the yellow zones. These values can be also tabulated. And it's very easy to create reports or results. In the near future, we'll make a webinar to demonstrate such features. Now see the stresses in the reinforcement steel. Now we see the stresses in PSI. We can also see the results in table form. We see the results by elements. Here we can see the results of the maximum principal stresses. We see the location of the greatest application of stress at the supports. In the next design, we will have CivilFEM provide us with the optimal design of this basic model. Now we're going to see the results of the load spectrum. Now if we load the file, we can choose the units. And we can see the deformation due to the lateral loading of the spectrum defined. Now we can do linear combinations of the solved separate cases into any case of our choice. In this case, we'll combine the results of the seismic loading, which is spectrum, and that of gravity. In the file open, it shows the different modes available. We selected the 6 mode. We have imported the normal modes and corresponding frequencies and deformations. We can see the list of the information at this point. We're going to demonstrate graphically the deformed model averaged. Yes, you can see how the deformation of the model occurs as a result of the combination of the spectrum and the dead load. Self-weight. I apologize. This represents the just the 6 mode. Now we see the periods of vibration of the model in seconds, and frequencies, which will be the reciprocal of the periods, in hertz. Now we're going to demonstrate how to make combinations. In this case, we can create our own combinations. We give it a name to the combination just created. Then we add it. And we can apply a load factor desired. Well, in this case, we'll use 1.2 for the LN and self-weight. For the spectrum, we'll use 1.7. And we click check. And then we can save this load combination. In other cases, we'll save it. And we'll search for them to see the results. Now we choose a unit of our choice. And we plot the results. Here we can see the displacement of the X component in inches of the combination just described. Notice this is a post-process step in which we're just using results of the analysis.